the field, you need to know what is a vector space. So, knowing these two, given that we have the history or the theory of, first, we know algebraic structures. We have done these for the past weeks. Secondly, we know of matrices. Thirdly, we know of the polynomials, those equations of x squared plus x plus 1 and so on, polynomials. And also, we can think of the integrals, we can think of derivatives, and so on. So such things can be used to determine a vector space, or to just in general we look at a field or so on, or just a definition. So we can also look at complex numbers, right? So and so on. So since some of these things we remember them, and some, if we don't, we're gonna be doing revision on them. But based on matrices, for sure, we've been going through it in and out. Now, if everyone knows how to multiply, how to add vector matrices and so on, it will be simple. So first thing that we look at is a field. So when we come to the first definition, we see that they say that a field F is a non-empty set. So when we talk about these sets, they should be non-empty sets. They should contain some element in there. It can either be a one element. It's like a vector space. When I talk about a vector space space should always contain a zero vector. So it means that it should at least contain one element, which will be the zero vector. You see right now? So they should always be non-empty. So every time you're defining a field, you define a vector space, you define a group, you define an abelian group, you always have to say it's a non-empty set. So they say that a field F is a non-empty set of elements called scalars with two operations, which the operations are going to be addition and multiplication, satisfying the following enjambs. So the definition of a field is similar to a definition of a vector space. You will see that you need these 10 enjambs. So if we look at this, we see that we need exactly 10 enjambs, and we'll focus on what do they mean and so on. So when we talk about a field, we are just referring, let me do this so I can zoom in. When we talk about the field, we are just referring to some set, or we can talk about, like for an example, real numbers, complex numbers, rational numbers, but then we decided to just denote them as F. Reason being is because fields can change. We can focus on the field of real numbers, complex numbers, and so on. So when we say that this is F, we are saying that we need these to be open for any kind of set. So now, when we come to the scalars, remember we said that this contains two operations which are called addition and multiplication. So when we come to this, the first enjamb, it's mostly, we can actually look at these two enjambs, which are usually contained also in vector space. When we look at this one, is closure under addition, or with respect to addition, and also we come to, let me check the one of a scale. Let me see, it should be somewhere here. Then we have this one of a scale. So what we do with this, the only difference between defining a field and a vector, remember with a vector, you need to take some elements. Let's say you take, when you're defining this one of multiplication, closure under addition, you take two elements which are part of V. And then you also take some scalar which are part of F, which is a part of F, right? And then when you take this, you can apply this. The first one you can apply it where? On saying that let's say I take these vectors, say A plus B is an element of V, right? This one will be under addition. Now I take this A multiplied by a scalar and say that will be an element of F. So this one is under multiplication, this one is under addition. We say right now. So whenever we look at them, we can just say, okay, this is closure under multiplication, is closure under addition. So this, since this is commutative, we can also say that even if I come and multiply this side, it will still be an element of F. Hence I say that these two are equal. You say right. So first thing that we can focus on is closure of both properties. We can look at them individually. So first, as I said, we look at the closure. Then we look. Next thing we're gonna be looking at is the inverse. Now, after looking at the closure, we can look at the additive inverse. For addition, there will always exist a 0, which is an element of that set, such that when I add 0 with some element, I'm going to get that element. And the same thing for this multiplication, there will always be some inverse, and that inverse will be 1 in this case for multiplication. You said that you don't have to write not equals to 1. You can just write there will exist one element of F such that when I take 1 times some number, which even if I multiply the left hand side or right hand side, there will still be an element of F. You see that? So in other words here we are saying that if I take like this, A times 1, I'm going to get 1 times A, which is equals to A. They should have said equals to A, but on the notes which I sent in the group, I did include this equals to A. You see right? And then, since now, first thing, remember we checked closure. Then secondly, we check both their identities. For the one of addition, you just write 0. You see here, you just write 0, then use addition. The one of multiplication, you replace 0 by 1, you use multiplication. You see that even this one here would have said 0 equals to this plus 0, which is equals to A. You see right, we would have even said that on this one, which is also correct. So now after checking their multiplicative identity, we can now look at commutativity. The reason why I'm taking them like this, check how I'm taking them. First I checked closure, then I check identity. Second thing, the third thing, I check commutativity. These are the ones which are mostly likely to be false. You see right, these are the ones which are likely to be false. That's why when the best idea or the best approach to take is the one that takes you to the shortcut of disproving something. Let's say they ask you, is this a field? And you find that certain enzyme does not meet or does not satisfy. It means that if it doesn't satisfy, then you can just conclude that this is not a field. You see right? So we always focus on the ones that usually most of the times they don't satisfy. So first we check closure, identity, and then we come to commutativity. For commutativity, we are going to take those two elements. We say this AB is an element of F, then we add, and like that. Then we see that this is commutative if it's the case. And then we also take the commutativity of this multiplication. AB equals to BA. You say right, if these are met, right, now we can go to this one of inverse. If these are met, we can go to this one of inverse. We look at the inverse of the addition. If it exists, this one is simple. You'll say, like, now check this. I want to check this between these two. For identity, you always start with they exist. You see right? Something for an element of F such that for an inverse, you always say for all. But some books, they don't differentiate. But then some of them which I've checked, they differentiate such matters. Even here, if we check identity, they say they exist. Then for my inverse, they say for all. You always start with that. So for inverse, for all a element of F, there will always exist something. So there's a difference between starting with they exist and also starting with for all. Even though at the end, all of them will be there. there's a difference between these two statements. Even if I say there exists something for all that, and also when I say for all something, there exists something, there's a difference between these two statements. I'm sure we've learned about them in those quantified statements in SMTH 012 and also SMTB 000. So now, since we say that every time we define an identity, we'll say there exists something. And also, don't forget, I'm saying every time we define, not when we are solving, right? But every time we define, when you are solving, you just let, but then you never let your identity to be numbers. You should let it be unknown terms. Like, let's say I say, I'm talking about matrices, right? Let's say I say, let A be equals to E1, E2, E3, E4. You see, this is allowed. But to let this be equals to, for an identity to be equals to this is not allowed. You don't let A be equals to this. This is what you're supposed to find. You said that. I'm sure they've already told you that in class. That when you're letting, it's better to let it be something like this. Then you come solve them. You say right. So that should always be the case. So these are one of the rules which you should be using across solving identity and inverse. So now after checking the inverse for both, you can check the associativity. You said that when you check the associativity with addition, you're just going to shift brackets. Let's say I say A plus BC, which is equal to, now I shifted this bracket to here, this side. You say right, you just shift brackets for associativity. And when you want to prove this, you don't start by saying this is equal to this. You can just maybe write required to prove. You write this statement equals to this, right? Then you start with one statement here. You show what is equals to. Then you do the other statement. You show what it is equals to. You say right now. So that is the simplest approach to take. So we check the associativity under addition. We also check the associativity under multiplication. So the associativity under multiplication, also you're going to shift brackets. If I have this, I'm going to shift the brackets to be this. You see, right? So remember, when we are proving this, we won't be referring to the laws. It means that the laws, we must know them by heart. You see, right? These laws, we must know them by heart. So after checking those, remember here we've checked all 5 for addition. And then when we come to this one of multiplication, we have closure, which is the first one. Second one, associativity, commutativity, identity. Also the inverse, we've already checked this. There are 5 there, you see right now. Then the last one that you can look at here, it's this one of the multiplication that distributes over addition, which we also have this in vector spaces. You're just gonna add the 2 elements, then you multiply by the one outside. Then this you can multiply it by this on the left hand side, also on the right hand side. You see right now. Then this will be the 11th property, which does not actually includes individual of these. It just includes both. You see that these ones up here, they were including this 5 were including only plus without multiplication, and this 5 we include in multiplication without addition. Then the last one includes both. You say right, you add the 2, you multiply. You say right, you add the 2, you multiply. So the last one is a mix of them both. So now, since you would have familiarized yourself with familiarized yourself with the properties of the field, now we can look at the ones of the vector space, because they're the ones that we're going to be using. Now here they say, the first example, they say show that the set of integers is not a field. Now for us to show that this is not a field, we can look for counterexample. You remember counterexample is used to disprove, right? We can look for counterexample. We can check which property might not meet. Usually for such cases, it can be this one, the inverse. But first what we can do, or sometimes it can be the identity, but we can check. they say it is not about the set of integers, so we can look at the integers. Yeah, sometimes it can be inverse and so on. So let's check. And then for us to show that there's no show that the set of integers is not a field, first we need to check. We need to do this. We're gonna let's say for us to show this, I'm going to let a be an element of an integer. Then I know that if I add two integers, I'm going to get an integer. We say right now has is closed under, yeah, let me say this is closed on integers. You see right now. So now we see that we have checked closure under addition, and then we check closure under multiplication. If I take these two and I multiply them, after saying that let a be an element of integers, we know that this will always be integers. And even if I multiply this, both I do this will always commute, and this is an element of integers. So this will be closed under addition. You said that, but I can just keep it like this to show that I'm just checking closure. So I can now say hence this multiplication is closed on integers. Now after checking the closure, remember a field contains addition and multiplication, right? It's defined by addition and multiplication. So I'm going to check the closure for both. After that, I can check. Remember I said that after checking closure, we can go and check the identity, right? Now after checking let's check the identity. Let's say now I say let's let a be an element of an integer. Then we have that a plus a is equals to a. Now we must find e, right? When I take a to the other side, I find that e is equals to 0. I ask myself, is 0 an element of an integer? You see, I can't come here and say let e be equals to be an element of z. I can come here and say, well, I can't come and say let this be an element of z, because I don't know yet if that number is going to be an element of z. You see, right? Another thing, I can't come and say let e be equals to 0, because I don't know yet if e is 0. I must prove it. So what I can do is just let z be let this be an element of z. That's what I can do. Now I find my e. After finding my e, I ask myself, is this an element of z? If yes, then I can say this is an element of z. You see where you can define this? You define it right there. Then I come and say, hence, let me say plus satisfies. I can say this satisfies the law of identity. You say that I say that this satisfies the law of identity. Now since I know that it does satisfy the law of identity and our identity is 0, I can now go to inverse of this addition. Now since we know that our a is 0, we can now go to the inverse. Now when I come to the inverse, I'll just let it the same thing, a be an element of an integer. You say, right, after letting a be an element of an integer, remember the definition says it says that for this to exist, we must have a plus under this addition, we must have a equals to this, and then this will be equals to a, and this will imply that a plus minus a will be equals to this is 0. You say right now, and then if we check, minus a will be equals to what? Minus a. If I take this to the other side, so it shows that if this is this case, it shows that now this minus a is indeed defined. So it means that a is the inverse of a is itself in this case. But this one won't help us get to the case, because we don't even know what is the operation of a. So the one that can help us get to the case in this one it's the one of multiplication. Let's go to the one of multiplication and see. First, for multiplication, since we've already checked that multiplication is closed, what we can do, we can check the identity of multiplication. We can say that since we have A, we can say A times E is equals to A. This is the case. Then we say that A will be equals to A over A is 1. And is 1 an element of an integer? Yes. Then you say, right, hence, you can maybe say hence the identity exists. You say right now. Now, since the identity exists, we can check inverse. We let A be an element of Z. Then the inverse is that we're going to have A times A this, which is equal to E, right? And we know that our A is what? Is 1. Now, when we check this, our inverse will be, so here I can just put implications so that I don't keep my at least my operations should have a sense, right? This will be 1 over A. But remember, A is an element of an integer. You see, right? If A is 2, the inverse will be 1 over 2. Is 1 over 2 an element of Z? Can someone answer this? Is 1 over 2 an element of Z? Let's say A is 2. If A becomes 2, if A takes 2 in the integers, is 1 over 2 an element of Z? Let's see. Anyone? It's not, right? So it means that automatically this one fails. So that's why here they had said, show that the set of integers is not a field. Automatically this property fails. We know that it can't exist. You say right now. Therefore, that one can never be a field under multiplication. So under Z, this one won't be a field. So now we see. So you would just stop right there. So it means that there was no need to even do the identity for addition and the inverse for addition. You would have just found the closure for multiplication. You find the closure for addition. Then you go straight to identity of multiplication and inverse of multiplication. Then you automatically find the solution and you stop. Most of the times you find that it's 10 marks. You just take your free 10 marks. You say, right. Then, unless if they said show all the properties, right? So with these ones of a field, right? These ones of a vector space. Now I want us to look at something here. These ones of a vector space. So we can do this. I think we can do this. These ones of a vector space. So when we come to these ones of when we come to a vector space, so let's say we come to a vector space. When we come to a vector space, remember this one, we're going to talk about this as being a non-empty set. We're going to talk about this being a non-empty set. Non-empty set, and this set is denoted by V. You say, right? So this non-empty set, we are saying that we're gonna be saying that this non-empty set should be an additive abelian group. So this should be an additive abelian group. You say, right, this should be an additive abelian group. So now, since we know that this is an additive abelian group, what we can say is that when we say that something is an additive abelian group, it means that a abelian group, you remember this one should be closed under addition. Another thing should be associative under addition, should be commutative under addition, and then the identity should exist under addition, and lastly the inverse should exist under addition. Now these are the 5 properties from an additive abelian group. Now remember, a vector space is just a combination of additive abelian group and also a scalar multiplication. Actually, here we say that we are scaling. You say right. A scalar multiplication should also have closure under multiplication. We should have, so since we have closure, we can also have cases where, let me do this. Yeah, so since we have closure, we're going to have a case where we distribute. Most of the times we talk about distribution, but these ones I can show you how do you find them, right? These properties. So now let's look at them, then I'll show you how we find these. So first, these are the properties of a vector space. I can try to label them as they're labeled there, but there's no need for you to know things like v1, v2. But first thing that we know here, let's say first I say here, I say for let me say, I'll say v. Always I want us to use this notation, right? When you're talking about a vector, say v that, so that they can see this one is a vector. And always I want us to use this. You say, right, use u, v, w for vectors. Don't use a, b, c for vectors, right? And also for scalars, guys, please, I would request that for scalars you don't use things like a, b, c. Use these ones: alpha, beta, gamma. You say, right, I want you to use this for a field. So for us to define a vector space, we're going to take this v, u, w, alpha, beta. Then these three are going to be an element of a vector. Then these two are going to be an element of a field. Now, remember, this can be defined. We can define this from, let's say we define it, maybe we say v such that this is moving. Sometimes it can be r to r. Sometimes it can be r squared to r and to r complex number to something, right? It can be something like that. And then here we say that for v, u, so the first one, if I take u and v, let's say I take v plus u, I add them and I found that this is an element of v. It means that this is closed under addition. So this is closure under addition. Closure under addition. You see, right? The second one, after checking closure under addition, I can check associativity, right? Now let's say I say v plus u plus w. And I said that this will be equal to, most of the times it will be best if you check commutativity first. Let me see what they first checked here. Let's see what they first checked. But it's best if you start by checking commutativity. Here you see they started by checking associativity. And then they checked, let me see, what else did they check? They checked it's not moving. Yeah, you see what here they used, right? Here they use like alpha, beta for an element of v. But as for v, I don't want us to use alpha and beta, guys. I want us to always use u, v, w for this, because these ones we're going to take them as our scalars in most of the times, you see. So that's what we're going to be doing. So I think for that, we can look at it like this. So we're going to be using this. We say v, u, w. We just shift brackets. So this one, we shift brackets. You see that? And this will be the case for associativity. We say, right? Then v3, we're just going to check the identity. We check the identity. Remember, for an identity, we are saying that here, for an identity, obviously there should exist some properties, right? But then I'm writing this for the fact of saying that this is what we're going to be doing when we're solving, right? So now for the identity, if I take v plus E. Then I find that this is equal to V. And also if I find that E plus V is still the same as this one, then this will be for identity. You see, right? And then another one, this one will be for associative. Then this one will be for identity. And then when I come to the next one will be the inverse. Remember, the inverse, I can just take this plus U, or I take this plus minus V, which this will be equal to E. And it will still be the same thing if I take minus V plus V. You see, it will still give us E, which this will be for an inverse. Then these are not the ones which I'm interested in, because I know that most of the times these ones are simple to check, right? These ones we know them. These ones we know them most of the times, like commutativity, where you have V plus U, which this will be equal to U plus V. I'm interested in the ones for scalar multiplication, because these ones, they may seem to be new, right? These ones may seem new to most of you. First thing that you do here for scalar multiplication, you need the scalar and a vector. If this is an element of V, then you know that it is true. You see, right? And then for the second one, you can look at the associativity, right? When, let's say, you multiply two, let's say you multiply two scalars, then you multiply by a vector outside, which this would be scalar b vector. Which this would be, I think it's this property here. Let's see which property is this one. It will be this property. Let's see. Let's see, is it? Let me check it on the other side. So for this property, right, we can say that, let's say in most cases, when you can say, okay, let me see, you can take the one of associativity. Yeah, I think it's associativity. You can have this. Usually this one can be broken into two, right? This definition. So we can have, let's say I decide to take V. Let's say I take V, I take U from a vector, and then I take a scalar from a field. Then I come here and multiply. Let's say here I come and say here it's a field. I multiply two vectors, right? Well, let me start with V. Multiply two vectors, and then I get that this will be scalar times V times a vector, right? Or the other property, which I think you only do one of these, the other property which you would take one vector, an element of V, and two scalars, right? And then when you multiply this, let's say you have a vector outside, you have two scalars inside, then when you associate, this will still give you the same thing. You said, I think you're discussing only, let me see which one did I include. You're only discussing one of these in your level when it comes to vectors. I think it's, let me see. Yeah, you're discussing this one of taking two, where is it? Yeah, of taking two elements from a field, and then you take one element from a vector. You're discussing this one, which is, I think it's also here, if I'm not mistaken. Maybe not here. Why can't I see it? That was V, is it 6 or 7? Oh yeah, you see, right? Two from a field, one from a vector, which is the one which we're discussing here. So two from a field, this two from a field, one from a vector. So once we have this, we can say that we are distributing, or we associate. Actually, we really associate. So when I can say here is, the first one, you know that you're multiplying a vector and a scalar. The second one, you multiply two the two scalars, then by a vector. Then the third one, what you can do about this one, V8, what you can do here, you can just add two vectors. So I want to show you something here. You add the two vectors, you multiply by a scalar. The other one, you're going to add two scalars, multiply by a vector. So these ones you discuss both of them, but here you only focus on one. The one of multiplying two vectors, you don't look at it. Then after here, you remove this, which you'll get this, which is the case. So this will be V9. So most cases I do them like this. Let me show this. Let me erase this. I do them like this in most cases for me not to forget them. Most cases I start with this one. Let me show you. I start with this one of adding two vectors. Let's say I add V plus U. After closure, you say right, I add V plus U and multiply by a scale. And then now I come and add two scalars. Then I multiply by a vector. After adding those two scalars, I'm gonna remove the multiplication and leave I'm gonna remove the addition there and leave it like this. You say right. So I know which one, because this one sometimes will take two vectors by mistake, and in here we're not discussing that kind of a property. So I just start with adding two vectors. I know that I need to add two vectors. On the next one I need to add two scalars. Whenever I'm adding two vectors, I multiply by a scale. Whenever I'm adding two scalars, I multiply by a vector. Then I can also remove this and leave it like this. You see that? Then the last one will just be to say 1 times V should always give us V. So if we have this, we can now try to look at some problems there that were given, right? So if you're able to remember this, then you're good to go. So it's just a matter of remembering which one comes after which one. So you can use many methods as you can, but I also shared how do I remember them. So now let's see from the guide the problem that we have here, which is this one. They say if we are given R squared. So let me open from this. I added it here so that we can be able to add a page, and then we'll try to solve it. Let me see. Yeah. So we're given this question, right? They say R squared is equals to xy such that xy an element of a real number with addition and scalar multiplication defined by x1, y1, x2, y2, which is equals to this, right? And this for k element of R. In this case, V is the Euclidean two space. Guys, when we talk about two space, I saw something with you, some of you guys there, the tutorial. When you let this, let's say some of you say let y be an element of R, you are wrong, right? This is an ordered pair, is a two space, it should be exponent 2. Once you take 3 elements, this should be an element of 3. Once you take, this should be an element of Rn. You say right. So you see that you should be careful of how you take your space. You see this one, they say this is n space, which you can also take this up until xn, which is better for this case. So we're gonna be using this case instead of this one of dot dot, right? So now when we say this, so it's better to use the subscripts, because the subscripts are the one that allow you to use up until subscript n. So now this question, they say this is defined by this. So according to the definition, and also they gave us the scale. So every time you're given a scale and they want you to check if this is a vector space or not, after checking your closure, jump to the last property and see if it is satisfied. Most of the times this one is not satisfied. You see right now. But if it is satisfied, then you're good to go. So let's see. Now we have this. We can call this let me see, this is, yeah, we can call this the first one, which we can call this V, we call this U. So we can go prove that. So let me do this. The question says that r squared, which is equals to xy, such that xy is an element of R, and this is defined by x1 y1 plus x2 y2, which is equals to x1 plus x2, then y1 plus y2, and also the one of k, x1 y1 will be equals to kx1 ky1 for k element of R. So we can cut this. I'm doing this so I can cut it. So now I can paste it here so that we see how do we solve this question. So the question is like this, right? We're given this. Now what we first need to do here, remember we're given this question. First thing that we need to do, we need to check closure under addition. All right, we can check closure under addition. This is the first thing that we need to do. So I saw with you guys, you're saying V1, then you can don't just say V1, you must say closure under addition. Now for closure under addition, I'm going to let V be equals to x1 y1, and then I let U be equals to x2 y2, and then I let W be equals to x3 y3 for further these two for further use. You see, right? So all these are an element of R squared. You see, right? So I just let this be an element of R squared, and I take some scalar. Scalar should always be an element of R, or some it depends on what type of set we're talking about. So since this is R, always a scalar will be an element of R. So here the scalar they told us to take is K. So we're gonna keep it as K. And they told us here that it's for K element of R. So don't try to change things, use them as they are, right? Use the format that you're given. So first thing on closure, or maybe let me do this, or write this after letting this. The first thing I check closure. Check closure under addition. So for me to check closure under addition, I'm going to add two vectors. So I can add V plus U or V plus W, but it's better to add the ones that were added at first. So this is just x1. Don't skip steps, right? y1, x2, y2. And this, according to the definition says that I'm going to add the first two, then I put a comma, add the second two. So we should always look at the format, right? So this is just going to be x1 plus x2, then y1 plus y2. And if we check, these are ordered pairs, right? This is an element of what? An element of R squared, which this implies that though I took two elements, it's V plus U, these were an element of R squared. So this is closed, you see, according to that definition. You see right now, hence closure holds. So if closure was not holding, automatically this would not be a vector space. So since closure holds, we can now check the second one. Remember, first we can check this scalar. Usually if these are polynomials, you must check the scalar and see if it satisfies the condition. So since this is not a polynomial, even if we run to the last property, it will still be satisfied. So now we say this. We say that according to this, we can now check. I can just follow them step by step. Remember, after closure, we check associativity, right? I can just follow them step by step until we find the one that does not satisfy, or until all of them are satisfied. Then we check associativity. Under plus. So it's good to just let this here so that you don't make mistakes of they exist, something here right now, and so on. So now for associativity, you know that I'll need U. So what we are required to prove, or you can just write here, required to prove. What is it that you're required to prove? That if I have U plus V, or let me start with V. If I have V plus U plus W, this will always be equal to V plus U plus W. You see right now, that's what we are required to prove. So I can just start with this one because according to the definition we're given that. So I start with the right hand side. Let's start with the right hand side. The right hand side is what? This is V plus U plus W, which this will just be equal to, this one is x1 y1 plus this one is x2 y2 plus this is x3 y3. You say right, and this will be equals, according to definition we say that we are adding this 2, then other side we add this 2, right? And then this would be x1 plus x2 y1 plus y2. And then we have this. And then now we do the same, we add this and this, then we add this and this until we are done. So this will be x1 plus x2 plus x3 y1 plus y2 plus y3, and this is an element of what? Of r squared. You said that this is really an element of r squared because we have two sets, there is an ordered pair. So this is an element of r squared. Now we look at the left hand side. The left hand side would be V plus U plus W, and this would be, we know that our V is x1 y1 plus x2 y2 plus x3 y3. Then we start with the ones inside the brackets, x1 y1 plus x2 plus x3. I add this and this, and also add this and this. And then y2 plus y3. We say right, and this would be x1 plus x2 plus x3 y1 plus y2 plus y3, and this is also an element of r squared. But if we check these two are equal, it means that this is associative. We say right now, it means that this is associative. And then For this case, the third one would check commutativity, which is not commutative. Let's check identity. V3. We check identity. When we check identity, we are going to say here, so first thing what I'm going to do here, I'm going to let E be equals to, so this one, remember this is not just any identity, it's called a zero vector, right? Just going to let E be equals to E1, E2. You see, right? I'm not going to let them be 0, 0. I'm just going to let it be E1, E2. And then what's going to happen here is that if I have V, if I take V plus E, this should always give us V. You see? And this would imply that, yes?
I have a question.
Yes.
Back to associativity. Go back to that thing. You see, the last part where you said x1 plus x2 plus x3 is all of them there, the element of a real number squared. Is it possible that we can continue with that formula, exchanging the values, the expressions, going back to, like, I agree, you see that the first one says in brackets V1 plus U, in brackets plus W. Can we go back to exchanging the expression, going back to V, the last one, the one we got on the left hand side? Yeah, that one.
Yeah, you can.
Without proving both of them.
Yeah, you can, but the simplest, the cleanest way, I want us to write things that are going to be clean. You can, but the cleanest way would be to write both of them separately. You see, right? That one it's also fine, but then the question is, why are you applying associativity? How sure are you that it exists? You see? So when you are shifting this, it would be, let's say you are here now. You just start separating them individually. Let's say you start by separating, as you said, you start by separating these two. Obviously, they'll lead you to this. You say right now. But then this is you applying associativity while you're not yet sure that it exists. Even though some books apply it, it's also fine. But this is what I prefer. So you can either do that one or you do this one. As long as in class they do it, then it will be fine. And then with this one, we know that V is x1, y1 plus a1, a2, which is equal to x1, y1. And then this will be a1, a2, which is equal to x1, y1 minus x1, y1, and this would be equal to 0, 0. We agree right now? And this is also an element of r squared. So actually, initially I shouldn't have said that this is an element of r squared. Even if I didn't say it, it will still be fine. But we realize that this is an element of r squared. We can just say it at the end, say that this is an element of r squared. But even if we say it here, we're still okay, because we know that they're going to be 2. So now we see that we got 0, 0. Is this the 0 vector, right? So we see that this is the 0 vector. Hence, we can say hence the identity exists. Under addition and real numbers, we know that should always be 0, 0, unless if the equation changes. So we come to V4. After identity, we can check the inverse. We said that looking at the inverse, we can just let's say with the inverse, we already I think we have U, so we can use U for the inverse. So for the inverse, we can have v plus u, which this should be equals to this, right? Then this should be, already I've defined this in the previous example, so I don't have to define it here. This should be x1 y1 plus x2 y2, which is equals to 0 0. Then now what I need to do is find x2 y2, which this should be equals to 0 0 minus x1 y1, which this will be equals to minus x1 minus y1, and this will be an element of r squared. You see, right? So we know that the hence inverse holds or it exists. You see, right now. Then the fifth one, we can check the commutativity. So for commutativity, we know we can have v plus u. This is what we are required to prove, right? So I'm just going to say required to prove. I'm going to say required to prove. And then now I looked at the left hand side. Then this will be, we know that this is x1. What guys, did the link, are you still guys on the session? Because this one is asking me if the class has ended or not. Are you still around?
Yeah, we're still here.
Oh, it means that she was not attending. y1 plus y2, and then we see that this look, what am I, oh, it's fine. Let me do the right hand side. I wanted to do the method which you were saying there, but then you can also do it. It's also fine. It means that here you will change this of their positions for you to do them. Then you separate them after. And then this would be y1. This one is y1. Not y1, man. x2. It's x2 y2 plus x1 y1, and then this would be equals to x2 plus x1, and then this would be y2 plus y1, and we see that these two are equal, right? So it means that this thing is commutative. You see, right? So now we have checked all the additive abelian group. You see, right? We checked all the additive abelian group. So since now we checked all the additive abelian group, we could check also the scalar multiplication. So, but then let me see, let me do this. I don't know if I did, I think I did give you guys a clue on this. Okay, this one I did, yeah, I think this is exactly what it's here. You see, right, closure, you would check that, VS2, you check associativity, you check identity, commutativity, and then now we're going to check, you see V6, we're going to check the closure for that. So what I wanted to do, right, I think I've explained this because we're out of time. We're supposed to have this for like an hour, right? So what you're going to do, right, you look at these solutions, you look at the closure with respect to scalar multiplication. Since I've already explained what's happening, you look at the associativity of scalar. Remember, I said that here you can also start with two of them. You said that you can have, you can start with this one where you're adding two vectors. You can say that you are adding two vectors, then you multiply by a scalar, then you come to the one you are adding two scalars, multiply by a vector, and then you remove the plus at the end to have AB times a vector, which is this one. You see, right? Where is it? This one, associativity of scale. You just remove that plus. You see, and then the last one, you multiply your vector by 1, and if you still get that, you see that it holds. And then since they all hold, you can say that it's a vector space. Let me say, I think they all hold. Yeah, they all hold. Then you can say that this is a vector space. So for now, I want you to try that tutorial right there. You can just try it, then you consult, you check with me before you go to class. So what you can do now, do this one. You do B. I'll be available even now if you want to consult. You do B, you do C. When they say V is equals to P, the set of polynomials in X over R with usual addition and scalar multiplication by A element of R. So you can look at this, then we see what we can get. You can look at n of this, doesn't matter which one. And then from there, you can be able to attempt the tutorial. But I'll also try to share the solutions to this tutorial before the tutorial tomorrow, so that you can be able to have an understanding of what's happening here, and also you can be able to know what to consult about on Friday. Also, if you attended the tutorial on Wednesday, you are also allowed to attend on Friday, right? You just not sign, or you sign twice. Then if you know that you need more understanding, because there's no time, next week you're starting with subspaces. Yeah, so I think I can just stop this.